Hi everyone, in this video I am going to go over the Wittig reaction. So just as a brief overview of the reaction, so we start with a carbonyl, it can be a ketone or an aldehyde, and then we also have our ylide, and then these two react to basically form an alkene. And the stereochemistry of the alkene, as we'll see later on, is dependent upon the stability of the ylide. But we will go from a carbonyl to an alkene. And we will also kind of get this molecule right here, this pH3P double bonded to O, and the P double bonded to O bond is very stable, which is a good thing. And so the first step is forming the ylide. So what we have to do here is we have to have an alkyl halide, and we have the PPH3, and it will attack the alkyl halide in an SN2 fashion. So obviously the same rules of SN2 apply. We want to have a primary alkyl halide so that we have like the least steric hindrance. And then we will get this structure right here. And the phosphorus will have the positive charge. And then we will use a base. In most cases, I believe that we'll use N-butyllithium, but we could also use, I think, sodium hydride, something like that, to deprotonate this one of these hydrogens right here, and it will go on to form a carbanion. And so we can see that structure right here in the Zwitterion form where we have the two charges next to each other, but we can also show resonance and get this ylide right here as well. You can really show either of the forms, but I prefer the Zwitterion form just so that we can kind of draw the lone pairs doing the attacking, just so we can kind of keep track of everything a little bit easier. So yeah, I think the next thing that confuses a lot of students is the stereochemistry for predicting the products. And we need to kind of dive deep into what is the more stable alkene. And we need to remember that the E alkene is more stable. And so if we have a stabilized ylide, we'll form the more stable alkene. And so we'll see some examples. And then if we have a destabilized ylide or something that's not stabilized, we will get the Z alkene. And so the reasoning behind that, at least the way that I like to think about it in my mind, is that if we have a stabilized alkene, it can be a little bit more picky and it can form the better product. And so we call this our thermodynamic product because in the end, it's going to be more stable. But if we have a destabilized ylide, it doesn't like where it's at now, so it will just react with anything it can. It's not going to be picky. It just needs to change from whatever it is right now. And that's how we end with the Z product. Even though it's less stable, it's kind of the quickest route. And so that will be our kinetic product. And so I think a lot of times students get confused with what is a stabilized versus destabilized ylide. So if we kind of look at this generic skeletal structure right here, if we have an electron withdrawing group, that will stabilize the ylide. And the reasoning behind that is because we have a negative charge right here. And if we can, push that around and we can give some of that negative charge to the electron withdrawing group, that will make it so that this carbon right here doesn't take the full force of the negative charge. It can kind of move around and it won't kind of make that negative or make that carbon super duper unstable by having all of that negative charge on that one carbon. And so if we want to destabilize our ylide, we'll add an electron donating group. And this will actually kind of add fuel to the fire. So it's already negative, it's already unstable. So if we add more electrons to the system, it will make the ylide even more unstable. So with some examples, we have a stabilized ylide because we can draw this resonance here. And I'm not going to go ahead and draw out the resonance structure just because I don't have space. But we can draw resonance, and so the negative charge is delocalized. It doesn't stay on that one carbon. We can also have a nitro group, and again, I'm not going to draw out the resonance, but we can show that it's kind of pulling the negative charge away. And then in cases where we have a destabilized ylide, in this case right here, I feel like this is a very, very, very common case. And I think a lot of times, students may not really make the connection that this methyl group is an electron donating group. And that's because methyl groups are sigma donors. So they will kind of donate electrons into a system through their sigma bond right here. And so we have a negative charge, we have a methyl group, it's going to donate electrons through its sigma bond, and so it's going to destabilize it further. Or we also have this ether where we can add more, again, more electrons, adding fuel to the fire, making it more destabilized. And so again, with the destabilized, we would get the Z alkene, the thermodynamic, it just wants to react and get it over with. Whereas the stabilized ylid, it can kind of be a little bit more picky and form the thermodynamic more favorable alkene product. So this is actually an example that I feel like is a really good one because we have to ask ourselves, not only is there resonance, but is there good resonance, right? So everything on this is a spectrum. It's not like we'll only get E and only get Z. We will kind of form a mixture of both. And in some cases, we may form more of the E alkene than in another case. We may form more of a Z alkene than in another case. But in this case, if we draw this Wittig form, we can see that we have a negative charge next to a benzene ring, which is normally very stable. But while there is resonance, the resonance is not super duper beneficial. And what I mean by that is if we go ahead and we draw a resonance structure, let's just draw this one. So we have this. We've moved the negative charge around the circle, we've delocalized, but even if we go one more position, we can, draw more resonance structures, but at the end of the day, we're basically just shuttling this carbon or this negative charge from carbon to carbon to carbon. So although it's, not staying with one carbon, it's staying on a carbon. And that's, while it is helpful, it's not good enough to get us an E alkene. Whereas before, with this example, even though we only have one resonance structure, when we draw it, the negative charge is now on the oxygen, which is much, much, much more preferred than just kind of moving the negative charge around on carbons. Because oxygen is more electronegative, it's better able to accommodate that negative charge. So I think that that's really all there is to the stereochemistry with predicting the products and the stability of the ylids. So now I just kind of want to briefly go over the mechanism, and this mechanism is a little bit wonky, so I'll try my best. But so again, in this case, we kind of start with the ylid. We want to form or draw this Wittig form just that we can again see a little bit better as to what's going on. And so this carbon will attack the carbonyl, pushing these electrons up onto the oxygen, and we get this intermediate right here. And so the negative charge on the oxygen is going to be attracted to the positive on the phosphorus. And so it's going to basically kind of make this square-like shape right here. And so this is where it gets a little bit tricky to keep track of. So this sigma bond right here will go to create the pi bond between these two carbons. And in order to not violate the octet rule, we need to get rid of this bond right here. And so what happens is those sigma electrons go to form the pi bond between this phosphorus and this oxygen. So it's almost like we have bonds just kind of moving all over. So again, it is a little hard to keep track of, but hopefully, if you draw it out, you may be able to see it. And then we go from this structure right here to the alkene right here. And again, I didn't really add any R groups because we just talked about the stereochemistry, but we would need to look at the stability of the ylid and then kind of figure out what the product will be. So I think with these types of questions, it's good to, recognize first that it's a Wittig mechanism, and then figure out whether the the ylid will be stabilized or destabilized, so that when you can kind of go to draw the products, it's almost like a puzzle. So I'm going to try to do this and hopefully it works well, but it's almost like you're snapping the oxygen and the phosphorus kind of over each other, and you will get a product like this. So again, it's not the easiest to see, but you're basically just taking the two pieces and snapping them together. And then you would want to evaluate the stereochemistry, because again, it's the ylid that will determine the stereochemistry. So you snap them into place and then make any adjustments that you need to do based on the stability of the ylid. So hopefully that made a little bit more sense. I know that a lot of times people aren't super familiar with the ylid stabilization and the fact that methyl groups are sigma donors. So again, they will donate negative charge through their sigma bond, and it will go to destabilize the ylid. But if we have an electron withdrawing group where we can draw resonance, that's important, I guess. It will go ahead and stabilize the ylid. Whereas even if we're just shuttling around the negative charge from carbon to carbon, while that may help, while we may get more of an E product, like in this case, we may get more E product than we would get in this case, the Z product is still going to be favored because we don't stabilize the ylid enough. So, if you have any questions about this, feel free to reach out. But good luck.